The ocean floor has been sending us signals for years, and until recently, nobody could explain what they meant. Instruments picked up chemical readings that made no sense. Rocks behaved like batteries. Oxygen appeared where oxygen should not exist. This is not science fiction. This is what happened when a space agency decided the fastest way to understand other planets was to stop looking up and start looking down. For most of human history, the deep ocean was treated as empty space, a cold, crushing void separating the world above from nothing at all. Sailors mapped coastlines. Fishermen understood the shallows. But past a certain depth, the ocean became unreachable, not because no one was curious, but because the physics made it nearly impossible. At the deepest point on Earth, the Challenger Deep in the Mariana Trench, the water pressure exceeds 1,000 times what we feel at sea level. That kind of force does not simply resist exploration. It destroys the tools built to attempt it. In May of 2014, that reality asserted itself in the worst possible way. A remotely operated vehicle named Nereus, built by the Woods Hole Oceanographic Institution, was several miles down in the Kermadec Trench near New Zealand, conducting one of the most ambitious deep-sea missions ever attempted. Nereus had already proven itself. It had reached the Challenger Deep in 2009, one of only a handful of vehicles in history to do so. Then, without warning, contact was lost. No distress call. No gradual signal loss. Just silence. Researchers later concluded that the immense pressure at that depth had caused an implosion, destroying the vehicle in a fraction of a second. Debris later recovered confirmed what engineers feared. A machine worth many millions of dollars, representing years of design and testing, was gone in an instant. That failure did something important. It forced oceanographers and space scientists to rethink their entire approach to extreme environments. Building one flawless, irreplaceable machine and sending it into conditions that could destroy it in seconds was, by definition, a fragile strategy. If that single vehicle failed, the mission failed with it. So a different question began to circulate among researchers at NASA's Jet Propulsion Laboratory and their oceanographic partners. What if, instead of one perfect robot, you built many small, expendable ones? What if failure was expected, even planned for, so that the loss of one vehicle meant almost nothing to the overall mission? This is where NASA's involvement stops sounding strange and starts making sense. NASA was never trying to become an oceanography agency. Its interest was rooted in a very specific problem. How do you explore an ocean you cannot see, cannot breathe near, and cannot return from easily? That description applies just as well to Europa, one of Jupiter's moons, and to Enceladus, one of Saturn's, as it does to the Mariana Trench. Both moons are believed to hide vast liquid oceans beneath miles of ice, oceans that have had no contact with sunlight for millions of years. If life exists there, it will not be found sunbathing on a surface. It will be found, if it is found at all, in crushing darkness, under extreme pressure, powered by something other than the sun. Out of that shared challenge came Orpheus, a small, low-cost autonomous underwater vehicle developed through a partnership between NASA and Woods Hole. Unlike Nereus, Orpheus was never meant to be irreplaceable. It was designed to be light enough, cheap enough, and simple enough that losing one was a setback, not a catastrophe. Its navigation system borrowed directly from technology developed for landing spacecraft on Mars, the same kind of terrain-relative navigation that helped guide the Perseverance rover to a safe touchdown in Jezero Crater in 2021. Since GPS signals cannot penetrate ocean water, Orpheus had to learn to recognize its surroundings the way a rover recognizes Martian terrain, using rock formations, ridgelines, and seafloor features as landmarks instead of satellite coordinates. Every dive Orpheus completed added to a growing body of evidence that the deep ocean was not a dead zone. It was one of the most biologically strange environments on the planet, and in some ways, one of the least understood. That strangeness had already been hinted at decades earlier, in 1977, when a team of scientists diving in the submersible Alvin near the Galapagos Rift made a discovery that quietly rewrote a biology textbook. Geologist Jack Corliss and his colleagues were searching for hydrothermal vents, underwater fissures where superheated, mineral-rich water escapes from beneath the Earth's crust. They found the vents. What they did not expect to find was life clustered around them in astonishing density. Tube worms taller than a person, ghostly white crabs, clams the size of dinner plates, all thriving in total darkness beside water hot enough to scald skin instantly. At the time, the assumption in biology was almost universal. Every ecosystem on Earth depended, in one way or another, on the sun. Plants captured sunlight through photosynthesis. Animals ate plants, or ate the animals that ate plants. Trace any food chain back far enough, and you would always find sunlight at its origin. The organisms clustered around those Galapagos vents broke that rule entirely. They survived through a process called chemosynthesis, in which bacteria convert chemicals like hydrogen sulfide, released from the vents, into usable energy. Sunlight played no role at all. An entire ecosystem was being powered by geology. That single discovery quietly changed how scientists thought about the possibility of life elsewhere in the solar system. If life on Earth could exist without sunlight, fueled instead by chemistry rising from inside the planet itself, then the frozen, sunless oceans of Europa and Enceladus suddenly seemed a great deal less impossible. NASA scientists and astrobiologists have pointed to these vent communities for decades as one of the strongest arguments that alien life, if it exists, might not need a sun at all. The deeper researchers looked, the more unusual the inhabitants became. Around vents in the Caribbean, scientists found blind shrimp that had abandoned eyesight altogether in favor of heat-sensing organs on their backs, allowing them to hover at the precise boundary between scalding vent water and freezing seawater, a survival strategy built entirely around detecting temperature rather than light. In other regions, researchers documented methane seeps, cold spots on the seafloor where methane gas escapes slowly through ancient sediment. Around these seeps, iceworms burrow through frozen methane, bacteria feed on toxic compounds, and mussels host colonies of symbiotic microbes inside their own tissue, turning their bodies into walking chemical reactors. Perhaps the strangest formations of all are the brine pools discovered in the Gulf of Mexico, underwater lakes sitting directly on the ocean floor, their water so dense with salt that it refuses to mix with the surrounding sea, forming a visible shoreline hundreds of feet below the surface. Fish that wander into these pools are effectively poisoned by the extreme salinity and die within minutes. Yet along the edges, dense colonies of mussels and tubeworms flourish, feeding on chemosynthetic bacteria in a landscape that looks, quite literally, like the shore of another world. And the deep ocean's contribution to astrobiology did not stop at the seafloor. In the mid-2000s, geomicrobiologist Tullis Onstad of Princeton University led research into microbial life found in water trapped nearly 2 miles underground in South African gold mines. That water had been sealed away from the surface for what geologists estimated to be millions of years, isolated from sunlight, from the atmosphere, from any connection to Earth's surface biosphere. And yet, inside it, researchers found living microbial communities, sustained not by the sun but by energy released through the radioactive decay of uranium in the surrounding rock, a process that splits water molecules and produces hydrogen the microbes could use as fuel. It remains one of the most self-contained ecosystems ever documented on Earth, a community of organisms that, in a very real sense, never needed the rest of the planet at all. Discoveries like these did more than satisfy scientific curiosity. They reshaped how NASA searches for life beyond Earth. Mars, once imagined purely as a dry, dead, red surface, began to look different once scientists considered that ancient underground water systems, warmed by residual geological heat, might still harbor microbial life sealed away from the harsh radiation above. Europa and Enceladus, worlds that seem, at a glance, to be nothing but frozen wastelands, started to look like some of the most promising targets in the entire solar system, precisely because their oceans mirror the conditions found near Earth's hydrothermal vents. To prepare astronauts for the kind of missions these discoveries might eventually require, NASA turned to the ocean directly. Off the coast of Key Largo, Florida, an underwater habitat called Aquarius has hosted a series of NASA missions known as NEMO, short for NASA Extreme Environment Mission Operations. Inside Aquarius, astronauts live for days or weeks at a time, conducting simulated spacewalks, testing communication delays, and rehearsing the kind of isolation and confinement they would experience on a lunar base or a mission to Mars. The ocean, in this context, becomes something closer to a training ground for outer space than a destination in its own right, chosen specifically because its pressures, its isolation, and its communication limits mimic conditions no other environment on Earth can replicate. But perhaps the most unsettling development in this entire story came far more recently, and it had nothing to do with life at all. In 2024, a research team led by Andrew Sweetman at the Scottish Association for Marine Science published findings from work conducted years earlier in the Clarion-Clipperton Zone, a vast stretch of Pacific seafloor roughly between Hawaii and Mexico. The team had lowered sealed chambers onto the ocean floor, nearly 2.5 miles down, expecting to measure the rate at which seafloor organisms consumed oxygen. Instead, the oxygen levels inside the sealed chambers began to rise. At first, the team assumed instrument failure. Oxygen production at that depth, without sunlight, without photosynthesis, should not have been possible by any conventional biological explanation. But the readings persisted across repeated trials, even after the researchers poisoned the samples to rule out microbial activity. Whatever was generating the oxygen was not alive. Attention turned to the seafloor itself, specifically to polymetallic nodules, dark, potato-sized mineral formations that litter vast portions of the Clarion-Clipperton Zone. These nodules form over millions of years and are rich in manganese, cobalt, nickel, and copper, metals in high demand for electric vehicle batteries. When Sweetman's team tested the nodules directly, they found something remarkable. Individual nodules produced measurable electrical voltage, enough, in some combinations, to potentially drive the electrolysis of seawater, splitting water molecules into hydrogen and oxygen through a purely geochemical process, without any need for sunlight or living organisms. The nodules, in effect, appear to be acting like natural geobatteries scattered across the seafloor. The implications of that finding reach far beyond a single stretch of Pacific Ocean. For generations, the presence of oxygen in a planet's atmosphere has been treated by astrobiologists as one of the clearest possible signs of life, a biosignature strong enough to justify searching for it across interstellar distances. If oxygen can be produced through a purely mineral, non-biological process here on Earth, that assumption requires a second look. A planet with oxygen in its atmosphere is no longer, by itself, proof that life exists there. It may simply mean the planet has the right geology. That discovery has also collided with a more immediate, more practical concern. The same polymetallic nodules responsible for this unexpected oxygen production are the target of active deep-sea mining proposals, companies seeking to harvest them at scale for battery materials as demand for electric vehicles grows. Researchers now warn that removing these nodules on an industrial scale could disrupt seafloor ecosystems that remain, in truth, barely studied, ecosystems that may depend on exactly the chemical processes the nodules appear to sustain. It is a strange and uncomfortable position for humanity to be in, chasing the raw materials for a cleaner future while potentially destroying a system responsible for producing oxygen in one of the last truly unexplored parts of our own planet. Taken together, these discoveries paint a picture of Earth that few people ever consider. Beneath the waves, in permanent darkness, under pressure that would flatten most machines built to withstand it, life has found ways to exist that have nothing to do with sunlight. Blind shrimp balance themselves against boiling water using nothing but heat sensors. Microbes survive for millions of years in isolated pockets of rock, powered by radioactive decay instead of daylight. Rocks, not living things, may be manufacturing oxygen in total darkness through nothing more than basic chemistry. Every one of these findings chips away at the idea that Earth's biology sets the only possible template for life elsewhere. That is the real reason NASA keeps returning to the ocean, not out of curiosity about fish or coral, but because Earth's deep sea remains the closest, cheapest, most accessible analog we have for alien worlds we cannot yet visit. Every vehicle sent into a trench, every sample pulled from beneath a mile of sediment, every strange reading recorded in total darkness adds one more piece to a puzzle that stretches far beyond our own planet. Somewhere beneath Europa's ice, there may be ecosystems running on chemical energy that would look, to us, almost exactly like the vent communities found off the Galapagos. Somewhere beneath the surface of Mars, ancient water may still be moving through rock, sheltering microbial life that has waited billions of years to be found. And somewhere in our own oceans, in places we have barely begun to explore, there are almost certainly discoveries still waiting that will once again force scientists to rewrite what they thought they understood. The question that started this entire pursuit has never really changed. It is the same question that sent Nereus into the chromatic trench, the same question that sends Orpheus back into the abyss again and again, the same question astronauts rehearse for inside Aquarius off the Florida coast. Are we alone in this universe, or have we simply not looked deep enough yet? For now, the ocean keeps answering with more questions than certainties, and perhaps that is exactly why NASA refuses to stop looking down before it looks up again.